Thanks. Yeah, I wanted to just briefly share some very recent results on experimental evaluating this idea of having self-optimizing or self-learning agents that apply to deep research. It's joint work with Fernando over there and Arthur, who could not be here. So just a quick show of hands. Who here has used deep research? Not that many, I'm surprised. I like to use it every day, actually. It saves tons of time. So we work with a lot of very expertise-heavy users, users in research, for example, or in engineering, or in that have a lot of very complex knowledge about products and processes, for example, in chemistry. And so these chemical research engineers, they are typically not very impressed by RAG. They are not very impressed by these quick summary answers. If a chemical research engineer wants to figure out innovative methods to improve the structural properties of these two bio-based plastics, and you give them this answer, they'll be like, duh, I already knew all of this, right? So it's correct in a sort of information retrieval and accuracy sense, but it's not very useful for these people. So what they are looking for is something that gives them a much more comprehensive overview of everything that's been done inside their company, but also outside in the research literature, and that it will actually give them some new information that they didn't have before, and also a complete overview that they didn't miss anything. So that's where deep research comes in, which typically, instead of these very quick summaries that RAG does, produces a multi-page report which really digs down into many different angles, compiles it and summarizes it and gives it back to you. And this is the type of thing that really saves you hours. So I think the sort of simple RAG idea has already been kind of strawmanned and discredited enough here in this session. So you don't need just vector search to create useful answers. The typical sort of RAG pipeline has a lot more tools between the search layer and the actual user, using all kinds of tools to improve the relevance. A typical setup will look something like this, where you have a whole bunch of pre-processing before you actually fire any queries. Then you're going to fire queries using BM25 and different types of embeddings, and you're going to do numerology, as Stavros said, to combine them, and then maybe a re-ranker on top of that, and then another layer of LLM on top of that. And that's really kind of evolving into agentic search. This is kind of a very simple type of agent architecture. But if you want to do deep research, it will look a little bit more like this. You have multiple parts. Maybe a query writer will first fire very different queries from the initial user query, do lots of searches in the backend, then use some kind of evaluation framework, LLM-as-a-judge, to pick out the relevant documents and then discard the irrelevant documents and summarize that and then read through them and then maybe find new angles that still need to be explored in additional iterations until it converges or you run out of budget. So that's typically how deep research works. And it's a kind of took this picture from the keynote this morning where OpenSearch has been kind of optimizing for milliseconds. This is a completely different kind of animal. So these are these kind of systems where you have an LLM as an orchestrator and you have many different modules and they're iterating and they're retrieving thousands of documents and reading all of them. And this takes, you know, not even seconds, it takes minutes to complete. So this optimization on the millisecond becomes a little bit a moot point, but the point is you get a lot more value for the actual user because this will save them time through of reading through all of that. So a lot of these sort of systems, when OpenAI or Google DeepMind make them, they're kind of monolithic and they're trained using reinforcement learning. But if we make them for actual sort of practical applications, we make them by building prompts and tools into these kind of agentic chains and trying to do our best job to write these prompts. And so you can imagine that we probably don't have the most optimal system in place when we have done that kind of artisanal optimization. So how can you optimize any of this? Well, not with reinforcement learning. First of all, because we don't have access to the weights of those models typically, right? We use something like OpenAI or Anthropic, or, but also because we don't actually have a system which is differentiable, right? We cannot do kind of some kind of backpropagation with a reinforcement learning system. We have very discrete sort of prompt-based modules. So recently there's been a large surge in the research, AI research community on this agentic AI optimization with papers like MyPro and TextGrad and Darwin Gödel machine, and I will go into some of them just for a bit. But the key element here is that we're going to use the raw intelligence of the LLM as an operator to actually come up with an improved version of the current agent. So we're going to take the prompts and the architecture of the current agent, we're going to give it to the LLM, and it's going to produce a better version for us. And of course, that's better is determined by measuring. So this idea was introduced by this paper called TextGrad, which is kind of a very metaphorical play on backpropagation. If you have these multiple modules, you want to kind of take the outcome, and if there's an error in the outcome, have a LLM critique all the different agents that contributed to it in a kind of backpropagation-like way. The paper actually got published in Nature, so it got a lot of attention. And basically, yeah, it's backpropagating in kind of textual format. A recent paper, which is just from July this year, by a group at Stanford and Berkeley called JEPA, kind of makes a different spin on that by pulling something out of the hat which has been very popular in the 1990s, which is called genetic algorithms or evolutionary computing. So JEPA stands for Genetic Pareto Optimization. And in this very nice paper, they actually proved that this kind of LLM-based genetic algorithm stuff can do optimization of these multi-agent systems better than actual reinforcement learning under equal conditions. So they take a model called Quen, and then they optimize it using both ways, and they just get much better result. So I will spare you the details of that paper. You can find it on arXiv. I just want to throw some of our own experimental results at you here, where the light blue bars are basically the performance of the deep research agent when you give it a very simple set of prompts. It's like the starting point, right? It's not that great. And the light orange bars are our best attempt to use human optimization to do a really good version of this deep research agent as best as we can. And what we see is that with both TextGrad and JEPA, but JEPA is a little bit better, we are able to optimize the light blue bar to the dark blue bar, and that's like a huge leap. And it's actually as good as our best human optimized prompt, or even a little bit better. So that's extremely promising, we think. And just for comparison, we've also added the light gray bar on the right-hand side of each stack, which is like what some people do when they have a prompt and then they give it to OpenAI's prompt optimizer and say, like, just make a better prompt for me. That's not that as good as this genetic algorithm. So that's it. Just wanted to share that with you. So basically, we've done this benchmarking on a data set called Scholar QA, and the self-optimized agent outperform human-optimized. JEPA is better than TextGrad, and starting from a sort of empty baseline, is better than starting from already a very complex human-optimized prompt. And here are some examples where TextGrad is really kind of depth first. It makes very long chains of optimization. The Jetpack is kind of more breadth first optimization, which is kind of natural for this genetic or evolutionary style of search. And just want to close with this slide. We haven't done the evaluation of this yet, but this is also a very recent paper, the Darwin-Gödel machine, where not only the prompts are optimized, but actually code is written in the process that just generates new architectures for the agents, and storing partial agents in memory and retrieving them. So it's also a very cool piece of work by people from University of British Columbia. And that's it. So we think this is the direction to go. It's very exciting.
Any questions? I saw a hand up really quick back here.
Thank you for that presentation. Interesting question, though. Comes from using like coding agents recently. In this process, have you considered adding like the user back into the loop to maybe clarify a particular prompt in action?
Because this is kind of going from a synchronous, like waiting for the answer, to an asynchronous type of process. Typically, the user goes away and closes the tab, or goes drink a cup of coffee, or do something else in the meanwhile, right? These things take minutes. So just coming back in the middle of that loop and asking them for feedback is not probably very productive. But what we have seen is that if the initial question is not clear, like asking for a clarification right away makes a difference.
I think we have time for one more question. Whose hand goes up the fastest? I thought so.
Just a quick question, maybe I missed it. What's the difference between like the in-depth and breadth? Yeah, I forgot what was the... Yeah, these two, between TextGrad and the other one. Like, where is the main difference here?
So TextGrad is like literally modeled on backpropagation. So it tries to find like the steepest gradient of descent. So like the single step that will make the biggest difference right now. Whereas this other approach, which is genetic search, it will actually maintain a population of like pretty good candidates, and then recombine them in all kinds of different ways. So this type of search is much more looking in parallel at different combinations of optimization. And actually, on this data set, it turns out to be better and faster than TextGrad.
Thank you, Jacob. Thank you so much. That's it, folks.